Hello, good morning, everyone, and welcome back to CS300 Introduction to Algorithms. And I've posted on the chat the questions for today's quiz. So let me repeat the questions orally. So consider the following families of graphs: the complete graph on n vertices, the circle graph on n vertices, and the hypercube graph of dimension d. And the question is, what degree do these graphs have? What is the diameter of these graphs in dependence on their number of vertices? In particular, for the last case, for the d-dimensional hypercube graph, please do not specify it in terms of the dimension, but first calculate the number of vertices and then determine the quantity, degree, and diameter in terms of the number of vertices asymptotically. Okay, so much for the quiz and attendance check. And while you please keep answering the question, let me fire up the slides so that we can resume the lecture. So, right. The classes of graphs that comprise the quiz are among the following families that we've discussed in the previous lecture. The complete graphs you can see illustrated in the bottom of the screen. The first 6 complete graphs. The circle graphs are indicated here. The hypercube graphs are depicted here, dimension 1, 2, and 3. Up to you to imagine higher dimensions. Then we have here the complete bipartite graphs. And here we have a grid graph. So, and while you keep thinking about properties like degree and diameter, let us also recur the property of being a planar graph, which is not a quantitative, but a qualitative property. Yes or no, is the graph planar or not? And as I kept emphasizing, this is not a question whether a graph is drawn in planar, but whether it can be drawn in a planar way, that is, whether it can be drawn without edges crossing. And to illustrate that point, let us recall particularly the complete graph of 4 vertices, K4 indicated here. The way it is drawn here, these 2 edges, diagonal edges, do intersect. So this is not a planar drawing of the K4, the complete graph and 4 vertices. However, the graph K4, the same graph can be drawn in a different way that avoids edges crossing. And that's what matters. Not how we draw the graph, but planarity is a property inherent to the graph itself rather than the drawing. And that's what you see here. This is the same graph, but now it's drawn without edges crossing. This is the graph with edges crossing, and this is the same graph. That's important. A message to notice, the same graph. And same for the bipartite graph when 2 and 3 vertices. The way it is drawn here, there are many edges crossing, but the graph can also be drawn in a different way without edges crossing, and therefore, so this is the same graph. This is maybe a little bit harder to see. So the 3 vertices on one side are here in the middle, and the 2 vertices on the other side of the partition, right, the bipartite graph, are now in this alternative drawing are located on opposite sides, not on the same side, but this is the same graph. The same graph, they have the same edges. It's just kind of like this upper part is being flipped down. That's one way of visualizing it in your mind. And so it's the same graph, but now there's no edges crossing, which means that the complete binary bipartite graph on 2, 3 vertices is planar because it can be drawn in a planar way. It can be drawn without edges crossing. Okay, so that's our recap from last lecture. And now we proceed to discuss some graph problems and algorithms for these graph problems. So we may have previously mentioned that before, but let me recall and recap the important parts of these problems. Namely, we're going to consider connectedness. More specifically, we're considering 3 types of connectedness. Well, 4 types. The first is the simple yes, no, whether it is connected, whether there exists a path from a given start vertex to a given end vertex. And this is a simple problem, but following our virtue of theoretical computer science, we make an effort to fully specify that problem. So here's the specification. Input is the graph given by its adjacency matrix. For now, we focus on we ignore possible weights on the edges, so it's just a 0, 1 matrix, and we're given a start vertex and an end vertex, where the question to be answered is the answer by our algorithm whether there exists a directed path from that start vertex S to the end target vertex T that uses only edges given in the adjacency matrix. So, and recall that we generally talk about directed graphs. So if we want to consider the same problem for undirected graph, we use our usual kind of reduction. Namely, we consider an undirected graph as a directed graph where to edge in one direction is also an edge in the opposite direction. So put differently, an undirected graph is one where the adjacency matrix is symmetric. So, or put even more differently, it means that the directed connectivity problem that we consider here is the more general problem, and then any algorithm that can solve that can also solve the undirected problem. So we're most general here. Right, so and the algorithm that we have discussed, let me recall it, is basically a stop algorithm that first indicates, marks all vertices as unvisited, and then makes a call to the recursive algorithm depth first search. We could also use breadth first search, but breadth first search is arguably uses a queue data structure, first in, first out, and depth first search does not use any advanced data structure. Well, not explicitly. It is a recursive algorithm, so it does use a stack, first in, last out, last in, first out, but only implicitly in making its calls. But anyway, so depth first search, once all vertices are marked as unvisited, looks at the given vertex, the start vertex. So the graph G under consideration is implicit in the depth first search algorithm. It is not modified, it does not change. Therefore, we refrain from passing it on and back and forth as argument, but instead focus on the argument that is changing, and that is a current vertex V. And if that vertex has already been marked as visited, then we abort this part of the depth first search, this part of the search. If the algorithm is the target vertex, then we return true. We have reached, we be able to reach the target vertex, and otherwise we mark the current vertex as visited, and then recursively proceed to all the to the other vertices, the neighbors of the current vertex, and right. And if any of these vertices, from any of these vertices, the target vertex can be reached, the target vertex is also considered implicitly in this algorithm. If from any of the neighbors, the target vertex can be reached, then also from the current vertex, the target vertex can be reached by transitivity, right? So from the current vertex V, since you are a neighbor, you can be reached. And if you, from you, target T can be reached, then it also means that from V, T can be reached via U. And if none of the vertices from the neighbors U, T can be reached, then T cannot be reached at all from the current vertex. So that's the logic behind this simple algorithm, graph traversal. And I'd like to emphasize two aspects. First, it is important that we assign marks to the vertices of the graph, marks that are initially labeled as unvisited, and only eventually during the course of the graph traversal, every visited vertex gets marked as visited, because this is the key to avoid infinite recursion. If the graph has a loop, then without these marks, the recursive calls here could get tied up in an infinite recursion, cycling through that loop back and forth indefinitely. But since we do assign marks to each vertex, that ensures that every vertex will be visited at most once, and therefore there's no infinite recursion. And from the perspective of correctness of that algorithm, there's no point in visiting any vertex second time, because the reachability, which vertices can be reached, if a vertex can be reached by some path, then it can also be reached by a simple path, a path which visits no vertex the second time. Let me repeat that important property, which is simple, but is kind of crucial underlying the correctness of that algorithm. If, let's say, T can be reached from S via some path, some directed path, then T also can be reached from S via a simple undirected path. And so the algorithm kind of implicitly restricts to simple paths. And this is what the marks kind of implement. So it's twofold. First, to avoid infinite recursion, and secondly, justified by since we can restrict to simple paths. Right, so that's, and the other aspect is transitivity. The other aspect to correctness of this algorithm, if the target vertex T can be reached from a current vertex V, if and only if there's a first vertex on a path to T, let's call that V, which must be a neighbor from U, and from which T can be reached. Let me say that again. It's kind of a decomposing and transitivity of reachability. From the current vertex U, T can be reached if and only if T can be reached from some neighbor U of V. So therefore, investigating whether T can be reached from all the finitely many neighbors of U of V, this is the recursive call here, determines whether T can be reached from U itself. So that's the justification for the correctness. And now we proceed and have a look at an animation of this algorithm. So what you see here is a graph where S is the start vertex and E is the target vertex. And this is such a recursive depth first search traversal through the graph. And so we proceed here. The first neighbor of S, there's only one neighbor of S, which is A. And then this algorithm in this loop, it's important that the order in which the neighbors are considered here does affect the further progress of the algorithm, but of course not the total overall outcome, whether it is reachable. So in this example execution, the neighbors of A are S. Yes, S is a neighbor of A, but S has already been visited, so it will not be visited a second time. Then the next neighbor of A is B. B has not yet been visited, so this is the next vertex that is visited, and that's where the recursion dwells into. So before even considering C and D as neighbors of A, the algorithm will first explore the connectivity from B to E. So next, the algorithm will consider the neighbors of B. And B has two neighbors, A and D. But again, A has already been visited at this stage. So it will proceed to visit D. And let me emphasize that from that on, D is marked. And when resuming the recursion of A, if resuming the recursion of A, D will not be considered anymore. But currently we're exploring the recursion starting at D, and the neighbor considered is D. And then from that on, the neighbors of D are G and F. So the algorithm will explore the connectivity from G, but G is a dead end. So it will backtrack and consider and resume connectivity starting at F. And from F on, it will reach E. And thus, this condition holds finally. And therefore, all higher levels of the recursion will also return true, right? If during this loop, one instance returns true, then so will all higher instances. So this is an example execution of the steps first search algorithm that in the end reaches E and therefore returns true. Yes, it is possible to reach from S to E. In this case, example of an undirected graph. So yeah, let's analyze the computational cost incurred by this algorithm. So the important observation is that every vertex is visited at most once. That's due to this mark that we introduce. And therefore, the running time is at most O of n, where n denotes the number of vertices, right? So in spite of all this complicated recursion, the running time analysis is pretty simple if you happen to find the right kind of invariant or cost property, namely the number of visited marks. And yeah, so on the one hand, the algorithm visits every vertex at most once, therefore it cannot use more than O of n steps. On the other hand, this simple analysis is tied because in the worst case, this algorithm will have to visit all possible vertices before finding the target vertex. For example, if the graph is simply a linear chain, right, then the algorithm must simply follow, that's the only way to follow that chain, to visit all vertices on the chain until reaching the end of the chain, the target. So to summarize, the computational cost of the simple algorithm is linear cost, and this is optimal because it has to look at all possible vertices. Right. So moving on, that was a qualitative property connectivity. And let me emphasize, of course, trivially, if we're not just interested in whether T can be reached from S, but the general question whether graph itself is connected, right? The universal property, whether from any vertex S to any vertex T, there's a path. This can be implemented by simply running this algorithm repeatedly for every possible choice of S and possible choice of T. And since there are n possible choices for the start vertex among the n vertices and n possible choices for the target vertex among the n vertices, that means the overall running time gets multiplied by the simple adapted algorithm with n squared. So since a single execution is linear cost of n multiplied with the n squared for all possible choices of S and all possible choices of T, that results in a total cost which is cubic n to the third. So that we have, together with this simple algorithm, we also arrive at a cubic cost algorithm for deciding whether the graph itself is connected. We'll return to that question when we now look at the quantitative versions of connectedness. So we're looking at shortest path problems, not as previously whether there exists a path, but well, also not whether there exists a shortest path, because if there exists a path, then there exists a shortest path. That's not a reasonable computational question to ask. What is a reasonable computational question? What is the length of a shortest path? Let me emphasize that it's also not a reasonable computational problem to ask for the shortest path, because in general, there may be several shortest paths that all have the same length. So the more important question, the well-defined question, is for the shortest length. The length is unique. The path attaining that length is in general not unique. So and here we ask for the shortest length of a path from a given start vertex to a given target vertex. So this is again like the various variants of the problem we considered previously, where either we have the start, so in this case we have the start and end vertex both fixed. So, and another generalization that we already consider here, because the algorithm will support this, is the weighted version of the problem. Not just the length, where we simply count the number of steps taken for a path from S to T, but the lightest path, the weight of the lightest path, where different edges may be assigned different weights on input. So this is a more general problem, and the restricted problem of simply counting is of course recovered by considering only adjacency matrices with 0, 1 weights. So the generalization involves also weights that exceed 0 and 1, other positive integers, and the emphasis is on positive integers or 0 if there's no edge. We cannot consider negative weights. That's an important observation for 2 reasons. First, because the algorithm won't be able to deal with negative weights, but also, and that is more serious, mathematically the problem doesn't make sense in general for when the edges may have negative weights. Let me expand on that. So imagine a graph with some cycles, let's say some triangle or quadrilateral, right? Some cycle in the graph. And let's suppose that the weight of the cycle, so adding the weights of the edges in that triangle or quadrilateral, results in a negative number, right? So if even if just one edge in that triangle may have a a largely negative weight. So then when adding the weights of the edges in that triangle result in a total negative weight for traversing that triangle once. And since it's a cycle, we can also, if there's a path that involves any vertex in that triangle, then we can kind of cycle through that triangle a second time, and thus decreasing the total weight, because every traversal of that triangle, single traversal, has negative weight. As another traversal adds more negative weight, that is decreases. So by repeatedly cycling through that triangle, we can make the weight of a graph of a path arbitrarily small, right? So, and this is a violation of the property that I previously mentioned as crucial for our search graph path search problems, namely that if there is a path, then there's also a simple path. This is not true if we consider weighted path. If there's a lightest path from S to T, or very light path, then with negative weights, that light path may require visiting vertices repeatedly, and therefore may not be a simple path. A simple path may have a larger weight in this case if we permit negative weights, which is kind of absurd, and mathematically, therefore the problem is not well defined, and so we're going to discard that. And that's another example on the importance of problem specification, right? So before even considering algorithms that purportedly solve a problem, first specify the problem. And here the subtlety, important but subtle, is that we can only consider non-negative integer weights. We'll discuss the question whether we can also consider non-negative real weights separately, but for now we only consider non-negative integer weights, because as I kept emphasizing, otherwise the problem is not even mathematically well specified, which is crucial, the first virtue of theoretical computer science. Oh, sorry. So anyway, a long sermon. So this is the first shortest path problem we consider. Given a start vertex and target vertex in a graph given by its weighted adjacency matrix, return the weight of a lightest path from S to T, or infinity if there is no path at all. That's a qualitative connectivity problem which we may also presume to have been solved already using the previous algorithm, right? So it's no loss of generality here to restrict to start and target vertices, which already have been verified and confirmed as connected using the algorithm on the previous slide, and now looking for lightest path in a refinement of that problem. So, okay, so that's a first problem we're gonna consider, and we're going to consider two more variants of that shortest path problem, and that's the next problem is where we only input the start vertex, but not the target vertex. So this is the second variant where we're interested. So this is all problem specification. We haven't discussed any algorithm for now. We'll come to them on the next slide. But the second problem for which we'll discuss algorithm is where there's a single start vertex, and the algorithm is supposed to output the weights, plural, of shortest or lightest path from S to any possible target vertex T. Okay, so in the first problem, we have two input vertices and the output is a single integer, right? In the second variant, we have one input vertex, not two, and the output is how many integers? N integers. For each possible choice of T, target vertex, of which there are of n many, For each such possible choice, output the weight of a lightest path from start to target. And so that's n integers output. It's a subtle but important point to emphasize. And the third variant of the problem, we have no vertices as part of the input at all. And we're asked to output the weights of the lightest path from any possible start vertex to any possible target vertex. So that's basically n squared, O of n squared, integers as output, and input is no vertex at all. And as you can imagine, any algorithm for solving the first problem gives rise to a trivial, naive algorithm for solving the second problem by running the first algorithm repeatedly for all possible choices of t, incurring a cost which of the first algorithm multiplied by n, namely for each execution of possible choice of t. But there might be also more efficient tailored algorithm for the second problem. Let me say that again. Any algorithm for the first problem gives rise to an algorithm for the second problem with computational cost increased by a factor of n, but there might be a tailored algorithm for the second problem with less computational cost. And similarly, any algorithm for the second problem gives rise to an algorithm for the third problem by simply running the second algorithm repeatedly for every possible choice of start vertex S, again incurring an additional factor of n in computational cost, but there may be a more efficient algorithm that tailored for the third problem that is more efficient than, let's say, n squared times running the first algorithm. So, and it turns out that this is the case up to some logarithmic factor. So let's now, once we have finally finished discussing the specification, which I keep emphasizing as so important, let's now proceed to look at the algorithms. Here are some algorithm for solving the first variant for the problem where we have a fixed start and a fixed target vertex. And so this is called Dijkstra's algorithm, classic algorithm. Yeah, this is standard topic in introduction to algorithms. So let me try to provide some intuition behind this algorithm. The intuition is illustrated here in this example graph. So in this example graph, we have a start vertex, which is called A, not S, and a target vertex, which is called B, not T, but anyway, that's just terminology. And the question is to find the shortest path or the weight of a shortest path from A to B. And if you look carefully, you can find such a shortest path. Any idea? How would you proceed from A to B? Let's stare at this graph a little bit. We're going to need some intermediate vertex, right? So 6 is a candidate intermediate vertex, resulting in a path of length 2. But the weight of that path is actually large because of this heavy edge, right? This is not a light path that uses this edge, but a heavy path. Of course, this edge has such a large weight, 14. And then using that edge adds another 9. And so we arrive at 23 for the weight. But as I kept emphasizing, this is a heavy edge. And can we improve that? Indeed, we can by using this apparent detour, right? It looks like a detour, but since it uses 2 edges instead of 1, but very light edges with weight 9 and 2. So the total weight of this detour is only 11 as compared to 14 with the apparent superficial direct path. So that's 11, and resulting in a total weight of a lightest path from A to B of 20. And question now is whether there's a even lighter path, and superficially, manually, we might try and find a lighter path and fail to do so. But Dijkstra's algorithm does so in a systematic way. It is an algorithm after all, that's the whole point. And so let me recall Dijkstra's algorithm again. We're going to use marks for the vertices which have been visited so far. And initially, all vertices are being marked as unvisited. And furthermore, Dijkstra's algorithm uses a priority queue. Priority queue, remember priority queue can extract, that's the most important observation, extract min, extract an element of least key value. So this is a little bit weaker data structure than searching and sorting. And so here we only extract, there's no insert operation. Initially, the priority queue is here initialized with all vertices, and the key values assigned to each vertex, right? There's the other operation called decrease key. So yeah, to be fair, this priority queue data structure, the motivation why it has been introduced at all, and its importance mostly relies on Dijkstra's algorithm, because this is exactly what Dijkstra's algorithm needs, right? It needs some data structure which allows to extract the least element, extract min, and which allows to decrease a key value. It doesn't need to be able to insert elements. It doesn't need to be able to increase the key value of elements. So therefore, these two operations are not part of the specification of a priority queue, only extract min and decrease key. Yeah, if you don't know where the priority queue comes from, this is where it comes from. Okay, so let's use that priority queue and discuss how to implement that and the computational cost of its implementation separately. So here it is, we initialize it with all vertices. And the intuition is, which is also enters into the correctness proof and the kind of loop invariant for Dijkstra's algorithm, is that this is the set of vertices which have not yet been visited. And then we also initialize all key values of all vertices with infinity, so that all the key values in the priority are infinite. And the first extract min operation can freely choose any vertex, well, except for the first vertex. No, that was wrong there. Let me correct that line. The start vertex is being assigned key value 0, so that the first extract min operation will surely provide and extract the start vertex. And the intuition that I'm trying to convey here is that the non-infinity key values are precisely the length of shortest path from start vertex to vertices which we have already been determined. Okay, let me say that again. So the algorithm basically kind of floods the graph. Imagine that this graph corresponds to some landscape, and the edges kind of correspond to, in a sense, the slope or the height, so that water that will start pouring into the landscape at point A will gradually rise, the water level will gradually rise, and try to follow the cheapest edges, the lightest edges. And we maintain the set of vertices which have already been flooded with increasing levels of water. And this is exactly what is in this the vertices which have not been flooded yet are the vertices that are maintained in this priority queue, the vertices that have not been flooded. And initially, no vertex has been flooded. And the first vertex that gets flooded is the start vertex, because, yeah, that's where we start, right? And these key values, imagine this to be the tentative distance from S. So the distance from S to S is obviously 0, right? And so for initially, we have not determined any distance to any other vertex. So we just assign to it the largest possible value indicated with a symbolic constant infinity. And then the algorithm has this loop. While the priority queue is non-empty, extract from the priority queue the vertex with least key value, the vertex with least distance from the start vertex. So in the first execution of this loop, it will definitely be in the start vertex that's being extracted here. And where any vertex that gets extracted will be marked as visited. Yeah, that's the point of having the marks, that we don't visit vertices twice. And then, so this is an indication of maybe some intermediate stage of the algorithm of the flooding process. So let's say that so far we have flooded the landscape up to the neighbors of the first vertex, these three, right? And so what will happen next? Well, that means, according to our loop invariant, we have the key values determined, the least distance from the start vertex to this one, and to this one. In this case, it's kind of trivial, right? So the least distance from here to here is 7, the least distance from here to here is 9, but the least distance from here to here is not 14, it's 11, right? Okay. And then in the next round of execution, the algorithm will extract the vertex with least distance. What is the vertex which has not been flooded and that has least distance? That is this one, right? This vertex has not yet been removed from the queue, has not yet been flooded. These have been flooded. And also this vertex has not been flooded, but these have larger distance, so larger key values, and therefore will not get extracted. The one with least key value will get extracted. That's a specification of the extract bin operation, and therefore this will be extracted next, will be marked as visited, and will be flooded accordingly, and then the distances will be adjusted according to now we know the least distance according to the loop invariant to this vertex, and therefore all other distances get adjusted with a decrease key operation. So let me illustrate that next part of the loop. So once we have extracted the kind of closest or lowest unflooded vertex from the priority queue and has been visited, marked as visited, we look at all the neighbors of that vertex that has just been extracted. Let's say this one. That's these neighbors, right? But only the unvisited neighbors, right? So these two neighbors we had already visited before, so the mark, they have already been marked. They will not be considered in this inner part of the loop. So there's an outer part of the loop which keeps extracting least keys from the queue, and then there's a in this queue inside this loop there's another loop that looks at the unvisited neighbors, and there's only one unvisited neighbor from here, and that's this one. And then see whether, since we now have more vertices flooded, and by the loop invariant all the vertices that have been flooded already know their least distance, right? Have been assigned the shortest distance, lightest distance from the start vertex. Now we have found a new vertex with optimal distance. Now that means we can possibly improve the distance of the neighbors of this vertex. Namely, if the distance from the start vertex to this vertex plus the distance from this vertex to the neighbor, that's adjacency weight adjacency matrix. If that is strictly less than our tentative distance from start vertex to the neighbor, then we choose that improved distance, assign that improved distance to the distance of the neighbor. Let me say that again. So this is a tentative distance from start vertex to the vertex V. And here we update this distance from start vertex to vertex V to those vertices which are neighbors of the vertex, current vertex U, of which we have right now know the shortest distance. So we look at these neighbors, and if the distance from S to the new vertex V plus the distance from that vertex U to the neighbor V is less than the best path we've found so far to the to V, then we use that improved path. So initially all distances are presumed to be high, and then we gradually decrease the distance each time we kind of find a better path, but kind of implicitly a better path by looking only at the final stage of that path, the stage from the current vertex to a neighbor. And so that means we keep on flooding, and for each neighbors of the flood, we look at which neighbor is going to be kind of flooded next, since we may have found a better, lighter, a lower path in this terrain. That's the idea of Dijkstra's algorithm. So here you see kind of an animation of that and how the flooding part proceeds. So the red part is that gets gradually flooded, right? So the algorithm repeatedly considers neighboring vertices and see whether it can find better path. And the red part is the vertices that have been removed from the queue, for which the optimal distance has already been determined from A. And once the optimal distance to B has been determined, once B is removed from the queue, then the algorithm is done. Okay, so that's we'll discuss the optimality of the correctness of that algorithm in the next slide. But first, let's do a computational cost analysis, shall we? And as I emphasized, the algorithm consists of two loops, nested loops, and let's estimate how often the outer loop is executed. So as you see, initially all vertices are put into the queue, and here in each iteration of the outer queue, one vertex gets removed. So that means it never gets inserted. That's not even supported by our priority queue. So that this outer loop gets executed n times for the outer loop. Then let's look at the inner loop. The inner loop looks at neighbors of the current vertex. And now that's an important but subtle point of this algorithm. In the worst case, the vertex U can have as linearly many neighbors, right? O of n neighbors is possible, right? Linearly many neighbors, which means that in the worst case, the inner loop can get executed as many times as n times for the inner loop, n times for the outer loop. And this repeated execution in nested loops does not add, but it multiplies, right? So that the worst case number of execution of the body of the innermost loop is, in the worst case, n squared. Let me say that again. The outer loop is executed at most n times, and that's tied, that analysis. The inner loop gets executed at most n times, and again, that's tied, this analysis, so that the innermost loop, in the worst case, gets executed n squared times. And while this is correct, this is in some cases, maybe in many cases, an overestimation. Let's discuss that analysis of Dijkstra's algorithm computational cost analysis. So as I said, in the first case, Dijkstra's algorithm executes the inner loop body at most n squared times. And again, this is in a sense tight because a graph that has n squared edges, any algorithm that finds the lightest path may in general need to look at all the edges, right? An algorithm that fails to look at some of the n squared edges may miss a particularly light edge that is crucial for a shortest path and therefore produce a wrong answer. So let me emphasize that argument again. It's an information theoretic lower bound. An algorithm that computes shortest path in general must look at any possible edge, right? Because if it misses an edge, then we could change the value of that edge maybe to 0, very light edge, and thus reduce the value of a lightest path, change the output of the problem, but an algorithm which ignores that edge, which fails to realize or change by re-executing, will produce the wrong result. So this is sometimes called an adversary argument in information theory. So that superficially it seems that n squared is the best we can hope for any shortest path algorithm, and that's in a sense that's also true, but in a sense it's also wrong, because that lower bound information theory, that adversary argument only applies to the case of dense graphs, to the case of graphs where all edges are actually present, right? But for classes of graphs which have asymptotically less than n squared edges, there's no point, there's no reason, there's no argument that forces an algorithm to look at the absent edges, right? So, and recall from the initial quiz today that there are many classes of graphs which do have much less than n squared total number of edges, put differently, which have less than linear degree, right? Yeah, so like cycle graphs or hypercube graphs. So that's what spurred actually Dijkstra's algorithm to be able to process more efficiently these classes of graphs which have less than n squared edges and which therefore may be amenable to shortest path calculation in Socratic time. More precisely, what we're hoping for and what Dijkstra's algorithm does achieve is a running time computational cost which depends on the number of edges of the graph. So that for graphs which do have full degree, which have quadratically many edges, there's no improvement, but compared to our naive analysis, but for graphs which do have less than quadratically many edges, there is an improvement. And this is what Dijkstra's algorithm achieves. And now we're going to look more closely at analyzing the computational cost, namely at analyzing how often the inner loop is executed. And the crucial observation here is that in the inner loop, every vertex may be visited repeatedly. A neighbor u of v may be visited again when the same u is also neighbor of a different vertex v prime, right? So vertex u can be the neighbor of v, but at the same time can be a neighbor of v prime. And so once no, the other way around. Vertex v can be a neighbor of u, but v can also be a neighbor of u prime. So when during some later execution of the outer loop, the vertex u prime gets extracted, then the neighbor vertex v will be visited the second time, apparently, although can be visited a second time because we have not marked it, right? So we only mark the vertices that are extracted, not the vertices that are looked at in this interior loop. But The important observation here is that in the inner loop, every edge gets visited only once. A vertex V can be looked at repeatedly, but an edge from U to V gets visited at most once. And that's important observation, which implies that the inner loop or the body of the inner loop gets executed at most m times, where m denotes the number of edges, right? So this is our improvement. When the number of edges is n squared, then that's the same as our initial graph analysis revealed. But when m, the number of edges, is less than n, then our more careful analysis shows that the body of the innermost loop gets executed at most m times, and this is not multiplied with n, the number of execution of the outer loop. So that the overall cost of Dijkstra's algorithm is n times for the execution of the outer loop. And the costly part of the outer loop is this extract min operation here. Extract from Q vertex with least key value, so that the cost of the outer loop is n times the cost of one single extract min operation. And the cost of the inner loop is m times, because the inner loop body gets executed m times, and in each execution there is a possibility for calling a decrease key operation. So this is the cost of the decrease key operation. So this is our improved and tighter and more careful analysis of the cost of Dijkstra's algorithm, n times the cost of extract min plus m times the cost of decrease key. Now, what is the cost of extracted min? What is the cost of decrease key? This is, of course, a crucial question that remains for rigorous analysis. But that question is actually turns out to be quite subtle and has been subject of research in the 60s and 70s with a consideration of several various variants of implementing the priority queue. So let me just say here that one naive way of implementing a priority queue is an unsorted array, right? So in an unsorted array, we can find and extract the minimum element in linear time by searching the unsorted array, finding the minimum element, and then by removing it, to which end we need to kind of put another element into the space that has now become empty. So that's linear cost for the extract min operation when implemented as a simple unsorted array. And the decrease key operation has constant cost in this case. We just need to decrease the value in that array position, which has constant cost, which results in the overall cost of n times n, right? N times the cost of extract min in an array plus m times constant. So that's returns our initial naive analysis of Dijkstra's algorithm n squared. As I kept emphasizing, when the number m of edges is quadratic, this is optimal. But when the number of edges is less than n squared, it might actually it will be not optimal. On the other hand, we will see that it's possible to implement a priority queue using some, let's say, binary search tree, where the extract min operation can be realized in logarithmic cost, right? Like the ABL tree that we analyzed and discussed previously. And the decrease key operation can also be implemented in logarithmic cost, so that the overall cost will be n log n plus m log n, which sounds, this is not the subject of the current course, though this will, what I'm saying now is actually more the subject of CS300 advanced algorithms. And the point here is we've already found a better, but there's even a more better implementation of a priority, which takes into account the trade-off between these quantities. but this is a subject of so-called amortized analysis of algorithms, observing that this second operation, the decrease key, tends to be executed more frequently. So we should, when designing the priority queue, we should spend maybe more effort in to reduce the computational cost of decrease key, possibly at the expense of increasing the cost of an extract min operation, because that may be executed fewer times than the decrease key operation. But this is not the, this will be discussed in CS500. So for now, that's all we wanted to say about Dijkstra's algorithm. And the emphasis here is that Dijkstra's algorithm actually also solves the second variant of the problem, which we have discussed, right? So we've discussed the variant where there's a start vertex and target vertex given and fixed. But Dijkstra's algorithm also solves the second variant where only a start vertex is fixed, and we're interested in the shortest or the lightest path to any possible target vertex T. This is also, actually Dijkstra's algorithm in the output in this array of distances dV for every possible vertex V contains the initially the tentative and at the end the actual lightest distance, the optimal distance from start vertex to any other vertex, including the target vertex. And since it includes that for any other vertex, it solves actually this slightly more general, this second variant of the shortest path problem, where only one start vertex is fixed and all possible other vertices are target vertices. Okay, and the third variant, as I kept saying, can be implemented using the second variant repeatedly by executing the Dijkstra's algorithm repeatedly for every possible choice of start vertex S, which incurs another factor of n in computational cost. So multiply that with n. So repeated, n times repeated execution of Dijkstra's algorithm also solves the so-called all shortest path problem from every start vertex to every target vertex, where the input is just the graph and the output consists of a list of n squared weights. But for this third version, there's a more efficient algorithm, which we'll discuss now, and that will be the last algorithm we discuss in today's session. So no, my bad. First, we need to talk about the correctness of Dijkstra's algorithm, and that will be the last thing we did discuss for this today. And the other variant of the problem will be subject in the next session. So let's discuss the correctness. And a popular way of asserting correctness of algorithms by by finding and asserting a loop invariant. And the loop invariant we consider here is that the distances stored in this array, right, the tentative distances, this is an array maintained by a Dijkstra's algorithm, will always be greater or equal than the actual optimal distance, weighted distance from S to B. So this is a mathematical quantity, and this is the algorithmic quantity maintained by the algorithm. And initially, this inequality is trivially true because initially the algorithm will initialize all these array entries with value infinity, remember, right? It was a initialization loop, so this inequality is true initially. And what we do want to prove now to assert correctness of Dijkstra's algorithm is that this inequality also remains true throughout the execution of the algorithm. That's why it's called a loop invariant, meaning it remains true, provided that it was true initially, it will still remain true for throughout every execution, every iteration of the loop. So let's prove that by contradiction. Let's suppose that there exists a vertex which violates that's kind of, sorry, that's kind of trivial. that this inequality remains true. What we want to prove is that after the execution of the algorithm, this will become an equality. That's the claim. Emphasize that again. Initially and throughout the execution of the algorithm, this inequality is and remains true, but the crucial claim is that after the execution, this inequality, greater or equal, will have become an equality. And we're going to prove that by contradiction. So let's make a proof by contradiction, and suppose conversely that there exists a vertex where this is actually a strict greater inequality, right? That's the opposite of what we want to prove, that this is an equality. It always is greater or equal. If it's not an equality, then it must be greater or equal. And we suppose that there exists such a vertex to contradict. More precisely, we consider all vertices which violate this equality and therefore have a strict inequality. And let's call that Zm, and suppose that it is not the empty set. Then consider the least element in that set, or more precisely, the distance from start vertex to a closest element in the graph. This is a mathematical quantity. This is a computational quantity. For all vertices in this non-empty set, this is where the hypothesis enters crucially, that this is a non-empty set. Otherwise, the minimum of an empty set is not well defined, or it's infinite, however you like. Anyway, since we presume that this is not the empty set, the minimum exists. It's a finite non-empty set. It has a minimum, finite non-empty set of natural numbers, which has a minimum, and that's called that delta. And since it's a minimum, not an infimum, it is attained. So there exists some vertex where this minimum is attained. And now we're going to look at the mathematical lightest path. It need not be unique, but by its very definition, this mathematical quantity means there exists a path from S to V, a lightest path. And we're going to look at the a vertex in this path right before reaching the target V. This, let's call that vertex U. And by the property of shortest path, it means that this initial segment from S to U is also lightest path from S to U. Let me emphasize again that important property, generic property of shortest path. If we have a shortest path and take an initial segment, then that will also be a shortest path. More generally, any subpath of a shortest path is again a shortest path. And this property is crucial and underlies the whole design and analysis and correctness of Dijkstra's algorithm. So it's worthwhile for me to repeat it a third and final time. Any subpath of a shortest path or lightest path is again a shortest or lightest path. So in particular, the path from S to U is a lightest path. By hypothesis, since we only consider edges of, oh yes, I should emphasize that we only consider edges of positive weights, right? So if the graph has some edge of weight 0, we first initially merge the two vertices. There's no point in distinguishing between two vertices that have distance 0, because we're talking about the undirected version of the problem, right? Directed, yes. So anyway, therefore, the path from S to U must have a weight which is strictly less than the path from S to V, right? Because the final step will have a positive weight, will contribute positively. So therefore, we have this strict inequality. And by the whole definition in choice of delta, delta is the least, but here we have found another contradictory point vector vertex U, which therefore cannot violate this inequality, right? So the distance from S to V is equal to the distance from S to U, which is the shortest path, plus the distance, the cost of the edge from U to V. And therefore, the distance from S to U is strictly less than the distance from S to V, and therefore it's strictly, it's not contained in the set M, right? Because the set M is only, this is the least delta, so this value is strictly less than delta. Delta is the minimum, so this value must not occur in this set here, and therefore U must not occur in this set M. And since U does not occur in this set M, the algorithm will correctly calculate the distance to U. Only the distance to V is by means of contradiction supposed to be calculated incorrectly. It's supposed to be overestimated, whereas the distance to U is estimated correctly. But then by the very definition of the algorithm of the extract-min operation, that means that U gets extracted before V, right? That's the definition of the extract-min operation. Extract the vertex with least key value, and the key value of U is, by our analysis, strictly less than the key value of V, right? And therefore U gets extracted before V. And then in the next iteration of the innermost loop body, that means that also the distance to V will get updated to the correct value as a contradiction to our hypothesis that the distance to V provided by the algorithm will be overestimated. So that concludes our proof of correctness of Dijkstra's algorithm. I understand this has been pretty subtle. This is where computer science meets graph theory, a very seminal marriage, if you like, graph theory. And before we've analyzed the computational cost of Dijkstra's algorithm as solving the one source, all target version of the shortest path problem, the second of the three versions. And that's all we could discuss today. And next time we'll continue discussing the third variant of the problem, all shortest paths for all possible pairs of start and target vertices. So yeah, that's all for today. Thank you very much for your attention and see you next time.